so today we have Jérôme Vandecasteele from Bielefeld University with us today, telling us about the theory of condensed dark matter. Jérôme was a student, PhD student in Brussels, and after that he was at TU Munich as a postdoc. And I think you moved to Bielefeld only in September or so, October?
Yeah.
So anyway, the room is yours. Please start.
Super. Thank you very much. I'm really happy to be here and to have the opportunity to tell you about our work. So thank you, Evan, for the invitation. And yeah, so this is I want to present work that I did towards the end of my PhD with my advisor, Michel Tilliat. And at the time, a postdoc, Raghu Gregorani, was in Brussels, and now he has a permanent position in IIT Madras in Chennai. And I'll try to keep it light, not to go too much into details, hopefully short. So, I do dark matter phenomenology, and I think it's kind of a good bet because wherever you look at in the universe, you see that dark matter is there; it's not going anywhere. And interesting thing that we don't know much about it, but we know how much there is at least. And I'm going to take the bet that dark matter is a particle, and I kind of do particle physics, and I like to think of dark matter as a particle because you can link it perhaps to other big problems of the standard model of our universe, such as supersymmetry gives you a natural dark matter candidate, and I'm going to mostly be talking about asymmetric dark matter, and so of course there is a natural connection with the visible sector asymmetry. And whenever one starts discussing dark matter, I think it's good to throw out some keywords that we know what to expect. So essentially, very broadly, dark matter can be classified by, for example, you can discuss dark matter phenomenology with respect to its interaction. So maybe we have the prototypical WIMP, just going to have weak scale interaction, or you can have very different candidates if their interaction are very strong. Nowadays, people talk a lot about self-interacting dark matter for problems at small scales, and sometimes you may even get dark matter candidates that have very, very feeble interaction with the standard model, maybe gravitational, something else. Then dark matter, the nature of dark matter, we don't know what it is. At least we can maybe list a few. So dark matter could be a boson, could be a fermion, fundamental particles, could even be, composites, a composite objects, or even something, even more composite than this is a collection of very, very large number of particles, and for example, such as primordial black holes. And then, you can always play around with the mass, and it's going to also direct you to different types of experiment. But so the prototypical WIMP would be a weak scale, or if you have boson, you can be ultralight, 10 to the minus 20 or so electron volt, or light or lightish. And then, of course, some challenges might come when you look at the asymmetry in dark matter. So, for example, if dark matter is symmetric, you might see it relatively easily in indirect detection experiment. But if it's asymmetric, like the standard model is, then it might be a bit more challenging. And so what I'm going to consider, fermionic particles that are going to be relatively light, that are going to be asymmetric and self-interacting. Essentially, I want to build up a medium of dark matter. And if it's light and asymmetric, I can get large densities and large chemical potential. And if it's self-interacting, then I can get interesting effects that emerges. And then I mainly want to discuss fermions. And of course, what's nice is that those properties you actually find them in neutrons. Neutrons are self-interacting fermionic, light, and asymmetric particles. If you think about dark matter, then it's very clear that dark matter can be. And then, of course, in other beyond the standard model scenarios, for example, neutrinos could also be self-interacting if you add some Yukawa interaction or something. And given these keywords, you could expect that it's going to have different behaviors in different systems than your vanilla WIMP. And so I want to discuss a little bit this today. So, one thing that I just want to look at one particular thing, and I will broaden a little bit more the scope, is that once you have all those keywords, once you go beyond the vanilla WIMP, then you can have the emergence of what I'm going to loosely call as dark stars. So it's going to be, self-gravitating configuration with a bunch of dark matter, and where, the gravitational collapse is supported by some internal mechanisms, for example, Fermi pressure. And if you want to build dark stars, then it's actually possible, and people have looked at it. So, for example, here this paper looks at a dark QED with only dark electrons. So you don't have dark positrons, so it's totally asymmetric. And in particular, it implies that you can't form bond states. It's going to help a little bit the discussion. And you can actually follow, the density, the evolution of the dark matter density of the dark QED density. You can follow its evolution, its contraction, its heating, its cooling, etc., etc. And you can actually show that such setup can lead to, the fragmentation of the dark electron halo into a bunch of dark stars. And I just want to show that, people have looked at it, and that, for example, in this plot, so this is the mass of the dark electron, which is a subdominant component of dark matter. This is the mass of the dark photon, which provides you a cooling mechanism. So this thing is dissipative. And for relatively strong self-interaction, so this is the dark fine structure constant, the dark contours are in solar mass, the sizes of the dark star that you are going to get. So for example, for 10 GeV dark electron and 100 MeV dark photon, you can get, dark star around the solar mass. And what's nice is that, this thing is as far as a typical WIMP goes. It's subdominant, it's asymmetric, it's strongly self-interacting, and then you obtain those compact, you can form those compact objects. And in those compact objects, hopefully, self-interaction are relevant, and I can tell you a little bit about which kind of effects emerges from there. But of course, this is one, let's say, family of dark stars, and I would like to expand a little bit the scope. I'm still going to call them dark stars, but it's going to be a little loose. So essentially, I'm going to look at things that develop a very large chemical potential, much, much larger than any temperature. And this thing can either be made out of fermions or bosons. And there's a very sure way to build those objects, for example, to accumulate them in neutron stars. So you have to imagine that, for example, you have an astrophysical object, could be the sun. I'm going to talk about neutron stars. So you have a neutron star, it is swept by the dark matter wind from the halo across its lifetime, which can be very, very large, like perhaps 10 gigayears. And as dark matter comes and interacts with the constituents of the dark star, it can be captured, then across multiple orbits can sink at the bottom, and then it's going to accumulate there. Especially if it's asymmetric, it's not going to annihilate away, it's going to accumulate. And the interesting thing, then there is a bunch of interesting signatures there. So for example, just dark matter coming and scattering on the constituent can heat the neutron star. Or if dark matter is heavy enough, what can happen is that the accumulated dark matter inside starts to self-gravitate, so it kind of become like a dark star, then can actually collapse. If you reach some dark Chandrasekhar limit, collapse into a black hole, and then this little black hole can grow and eat the entire neutron star. So another class of dark star is what I'm going to call accompanied. So it's going to be like a dark star which has a significant amount of baryons in it. Like, for example, this would be a dark matter halo. Then you can also have lonely dark stars, so dark stars that are kind of there alone. And it also has interesting signatures. So for example, even just in the solar system. So if we are lucky that the dark star passes near Earth or near the solar system, actually it could, for example, disrupt the very precise positioning of GPS satellites. And it's quite unlikely, but actually this thing is apparently enough sensitivity to detect such a dark compact object passed near us. And what I want to tell you about is that dark matter self-interaction can be relevant in each of these scenarios. Like for example, for transmutation, for transmutating neutron star into black holes, actually dark matter self-interaction might actually impede this end result. Or for example, in dark matter halos, if you could have very different prediction when it comes to the mass-reduce relationship of your halo compared to free dark matter. Then essentially the talk is going to be two parts. I'm going to tell you a little bit about what happens in a very simple theory, the Yukawa theory. Then I'm going to add superfluidity. It's going to lead to a very nice and self-consistent description of dark matter self-interaction and their effect in a medium. And then I'm going to conclude. So, the best thing is to start with free dark matter. So the way I'm going to do essentially QFT, so I think it's nice to start with a Lagrangian, and the way to discuss medium of dark matter. So dark matter at a non-zero chemical potential is going to be writing this Lagrangian with this little extra term. So it's psi bar mu. Mu is the chemical potential, gamma 0 psi. And you can see this, for example, as a term that would look in electromagnetism as A0 gamma 0. So A0 is going to be the scalar potential for the electric field. And so this is just a thing that would count the charge of the system. And here it just counts the number of particles that I have in my system. And already with this, just this addition, you can get Fermi pressure and very nice phenomenology. So, for example, you might build a dark matter halo composed of degenerate fermions, and it's going to, thanks to the development of Fermi pressure, is going to give you naturally cored profile for your dwarf galaxies halo. And then at the level of cosmology, actually, even if the fermions at zero temperature, because there is a Fermi surface, because there is a Fermi momentum, because they are degenerate, they can actually behave a little bit like warm dark matter, and it's possible to put constraints on these things. So already, such a setup is quite interesting. It's phenomenologically relevant, but it's going to be things can happen when you start adding self-interactions to the medium. So I'm considering the same fermions with a non-zero chemical potential, it's at finite density, and now I'm adding Yukawa interaction with possibly light, scalar bosons. And it's a very simple theory. It's essentially three parameters. I have the mass, I have the coupling, and I have the density. And what happens? You add attractive interaction, so your medium is going to react to it. So the best way to look at it is to realize that when you're at finite density, actually this operator here actually gets a valve. So this is the appearance of your medium. It gets a valve, and so if you look at this term as a contribution to the potential of phi, you actually see that phi gets a a linear term in its potential, so it's going to tilt the potential in one direction, and phi is going to obtain a vev, which is determined by the coupling, the Yukawa coupling, the mass of the mediator, and the finite density. And if you plug that back in, you see that actually this will show up as a correction to the mass. So now, we have a medium, it has self-interaction. It turns out that the fermions inside the medium, they have an in-medium mass that is smaller than the bare mass. And if I put it in a, if I put it in a little diagram, it kind of looks like this. So maybe you need to look at it like 90 degrees to the right. So I have fermions, I have here a propagator, and here I have a loop that is actually non-zero at that pole, that is actually non-zero at finite density. And this, just for jargon, it's not exactly the number density, but it's called the scalar density. And this is actually a very old story that emerged from consideration in nuclear physics. So if you psi, you call it neutron, and phi, you call it sigma meson, then the same thing follows. Then people have started to apply such effects in neutrino physics, cosmology, dark stars. And I want to describe a little bit what happens in more detail now.
Sorry, but
So,
what?
Yes.
Sorry, sir. Can I ask a question here?
Yeah.
What determines the size of that wave, or is it something you tune?
So, essentially, if you tell me I have, this number density of particles, the wave is going to be given by this thing. So it's totally determined by the medium.
Okay. Okay. All right. Okay. That makes sense.
So now we can maybe look a little bit at how the in-medium mass behaves. So M star is the in-medium mass, M is the bare mass. And here I give you the Fermi momentum divided by the bare mass, but it's just a nice measure of density. When the Fermi momentum is large, that means the density is large, and even it tells us that the Fermi surface might be ultra-relativistic or non-relativistic. So as here I give you an effective coupling. So this is the relevant parameters, the relevant combination of parameter that enters into the game. So it's G squared times dark matter mass squared divided by mediator mass squared. And so, for example, if this coupling is small, then I'm looking at the blue solid line, and I see that the in-medium mass is the same as the bare mass, the vacuum mass, until very large values of the Fermi momentum. But then it tells me that this medium is going to mostly behave the same as a free, as if I had no interaction, because the mass starts to become smaller in a region of density where, in any case, the mass wasn't playing much role. And so this is going to mostly behave like a normal Fermi gas. But for example, if the self-interactions are large, then even for systems that are supposed to be non-relativistic, I can actually find out that the in-medium mass is much, much smaller than the bare mass, and that this will impact a large change on my medium. And also, it's a bit different than the usual thermal mass. Whenever you put things at finite temperature, you tend to get things that are heavier, but here it's actually lighter. This is due to collective effects in the same way. And so this is how maybe one can see that the medium is impacted by dark matter self-interaction, but it doesn't really tell you what happens. And maybe the best way to look at it is to take a step back and do thermodynamics. So here I give you the pressure and temperature in quote phase diagram of the Yukawa theory. So here it's not really the temperature, but it's the inverse coupling, but you should expect that the inverse coupling behaves a little bit like temperature, because for example, if my coupling is small, then my particles are not going to feel much attractive interaction. And so it's going to be kind of like if it's a hot medium where my particles are not, close to each other. Whereas if I go to very large couplings, then my particles will want to stick together. It's a little bit like if the medium was cold. And so one can go and do, compute the pressure, the energy density in this theory. You do it from the partition function, and you obtain the free energy, and then you take derivatives of free energy, things like this. And so what you find at the end is that in this plot at large temperature, and so small coupling, the medium is going to mostly behave like in a way, what I'm saying here, there's almost a one-to-one correspondence to the phase diagram of water, because attractive interaction due to a Yukawa force is a bit the same as if you have attractive interaction through the Lennard-Jones potential. And so when the temperature is large, then you actually have an equation of state that is mostly polytropic. It is mostly the same as the usual Fermi gas. And then for self-gravitating configuration, what happens is that the mass of the cloud is going to be proportional to the radius to the -3. So this is the same thing that happens for neutron stars. But if you go to small temperature and so large coupling, what happens is that the equation of state completely changes. It's not polytropic anymore, but it's going to resemble that of a Bag model. So the Bag model, it's an old story. It's a phenomenological model that was used in nuclear physics to describe hadrons. Hadrons, you should see them as a potential well with free particles going inside, and this is essentially the same equation of state. It's just here that we got it from first principle, starting from the Yukawa theory. And actually, this equation of state describes something that is incompressible. So it's as incompressible as special relativity allows, but still incompressible, which means that the mass of the cloud is going to be proportional to its radius cube. And so this I'm going to call a liquid phase, because it's a high density incompressible phase, whereas this is going to be mostly a gas. I'm going to call it gas or fluid. And the phase transition between those two phases is actually first order, and the order parameter for this is simply the density, because the density jumps a lot between the gas and the liquid phase. And if you add self-interaction, now your dark matter might behave a little bit like a liquid, and so this is very, very different than vanilla WIMP. So the one way that you can use this, is to look at dark matter halos that are dominated by dark matter self-interaction. So I gave you, you can compute the equation of state. You can add gravity to the Tolman, Oppenheimer, Volkoff equation, and then you are now looking at hydrostatic configuration of this dark matter. And then you can compare what happens in the free case and in the case where you have self-interaction. So here I give you in this plot, so on the y-axis is going to be the mass of a dark star, in solar mass, and I'm looking at very large things, and in the x-axis is going to be the radius in kiloparsec. So the blue, the boxes are going to be the typical sizes of dwarf galaxy halo and the typical sizes of halo for large galaxy. Think, Milky Way, and you can do the exercise. What would a self-gravitating hydrostatic configuration of free fermion look? And those are the dashed line. And so if you turn off self-interaction and you give a mass to your dark matter of 165 eV, then as you change the central density of the halo, you move along this line. And so, for example, you see that such a dark matter candidate could reproduce a 10 to the 8th solar mass halo within a 1 kiloparsec radius. So this is the typical size of a dwarf galaxy halo. So if you go to lower dark matter mass, and so instead of 165, you go to 25 electron volt, what happens is that for the same dark matter halo mass, you actually go, you can't all fit them within 1 kiloparsec because of Fermi pressure. It's the halo is much more fatter, is much bigger than 1 kiloparsec. And so, in a way, this is a visual representation of the Tremaine-Gunn bond, where if the dark matter mass is too low, you just can't fit it inside your galaxy. But if you turn on self-interactions, what you have actually is this red line. So now, as you augment the central density, you actually go up in mass, whereas here, as you augmented central, you actually go up in radius. And so, for example, for mild couplings and very low electron masses for dark matter, you could actually reproduce dark matter halos that are, of the typical size of dwarf galaxy and large galaxies at the same time. So in a way, this is also again a visual representation of if you turn on self-interaction, you can actually violate the Tremaine-Gunn bond. And then, as a last comment here, what's nice is that in this line, there is no factor of G Newton. This is completely dominated. This is not dominated by gravity. This is completely dominated by self-interaction. And so, there's no G Newton. There is no mass Planck in this thing. And then, essentially, it kind of you can kind of represent the same. You can kind of represent the same the halos of dwarf and large galaxy because there is this somewhat weird coincidence. The average densities of halos for dwarf galaxies and large galaxies are kind of the same. It's just a curiosity. But so, and then what's nice is that this kind of looks like a neutrino, 0.1 eV. And so this would be, one way to use self-interaction to completely change the behavior of a dark star at the level of dark matter halos. But there's a small, let's say, there's a small thing that, at this level of description, everything flows correctly, but it's just that it wasn't totally consistent. So it wasn't totally the full picture. And now I want to discuss that you can actually add exactly what's missing. You have to pay the price of working a little bit more, but I'm going to discuss that all these objects actually exhibit a superfluid behavior, and that can be computed. And then at the end, I will show you, what happens to the expectation that we have built up until now. So I already, it's always nice to draw diagrams. So I already discussed this diagram, but then inevitably, you would also generate a diagram that looks like this. So whereas this was a correction to the medium mass, this diagram would actually describe the formation of Cooper pairs. And it hadn't been yet considered. And so we wanted to compute it, understand, can the formation of Cooper pairs, does it have any impact on the thermodynamics, etc. So people have been looking, discussing superfluid dark matter was there have been some work, and again this will arise because you have attractive interactions between your particles. And what's nice that in the Yukawa theory, actually, you can never avoid it. Like it's always there because superfluidity, the Cooper pairing, is actually it's infrared. It's an infrared behavior, and then it's a for the even for very very small self interactions, attractive self interactions, you would form these things, and of course, it's maybe I can call that beyond condensed matter in the sense that you can those are systems that are not usually Yukawa theory. It's not an electronic superconductor, so it's not something that you see in the laboratory, but still dark matter. The dark matter context allow you to explore such kind of theories, and also is the thing that these two effects, they go hand in hand, they affect each other, and so you may want to make sure that they affect each other a lot. Can I neglect one, etc.? They go hand in hand, so it would be nice to have a fully self-consistent description of these effects. And superfluidity, superconductivity, it's an old story, right? It's not just in dark matter. And I want to describe a little bit what happens in the standard model. So it turns out that, for once, maybe, for once in a while, the abelian case is a little bit more complicated than the non-abelian case. So, for example, if you think about electrons and their electric charge, actually, so if you talk electronic superconductors are going to be a little bit more complicated to describe because it's not really the exchange of photons between electrons that provide you an attractive interaction, but it's going to be the lattice, etc. And so I'm going to stay I'm going to treat the non-abelian case because it's a little bit easier to see what happens. And for example, in QCD, you have superfluidity and superconductivity phenomena. So, whenever one discusses QCD, you may want to ask, okay, it's a strong interaction. How do you even handle it? So, actually, this is one region of the QCD phase diagram where lattice really cannot help you because you have the numerical sign problem. You can't do lattice simulation at non-zero density, even at zero temperature. But if you go to very, very high densities, you would actually probe short distance. The interaction at the Fermi surface would involve large momentum exchange, and so QCD can be perturbative. And that means that you can treat these with the tools of QFT, and you can understand, okay, in this setup, why would those superfluidity or superconductivity arise? So if you take two quarks, actually there is an antisymmetric combination of color where the potential between the two quarks is actually attractive. And so if it's antisymmetric in color, they feel attractive self-interaction. Of course, pairing is going to be most active in the S wave because it's the situation where the quarks would spend the most amount of time closest together. But you know that the wave function has to be overall antisymmetric, so you actually need two flavors to realize superconductivity, color superconductivity in QCD. But you have all the ingredients. QCD provide you all the ingredients to have superfluidity, and people have looked at it a lot. And what's nice is that the QCD community has worked a lot on it, and then this has actually been fed back into the dark matter community. So, for example, Stefan Alexander and collaborators, they've looked at So stumped dark matter, so strongly interacting ultralight milli-charged particles. And essentially they have a dark sector that is just dark UCD. So two flavors, three colors. And you can actually build dark matter halos that are completely dominated by color superconductivity. And this provides you with nice flat, it provides you with completely flat dark matter density. So it's a nice thing for chord halos. And for example, outside of the halos where the density is a little bit smaller, then actually you would transition back into hadrons. So whereas your halo are made out of quarks, it confines outside the halos, and then you just get hadrons, and this just gives you a nice way to have a chord halo and then a nice normal dark matter density at larger radius. And the thing is, the Yukawa theory provides you also with everything that you need for superfluidity, because you have attractive particle-particle interaction because you exchange a scalar boson. Then, again, one S pairing, the S-wave pairing is going to give you the most possible attraction. And so you only need one species. And so it's a little bit easier to track. And so you can see this as, the one color, one flavor, spin zero limit of QCD. And it can be used as a toy model to understand color superconductivity. They share some properties. Before going a little bit more into details about superfluidity, because I don't know, I never really had this in undergrad, and I don't want to go too much into detail. I just want to outline some results, etc. But there's this thing that often, whenever I don't know, in the particle physics theory, people will tell you the broad-angular Higgs mechanism is the same thing as superconductivity, the same thing as the Meissner effect. But what's the parallel goes a little bit further than this. So, and I just wanted to outline this little neat fact. So, for example, you can look at the massless Yukawa theory with a heavy mediator. So now I consider something with a chemical potential with zero mass, and then with an attractive self-induction due to the exchange of a very heavy mediator. So it's like a 4-Fermi interaction. And now this thing is going to exhibit Cooper pairs. And so what happens is that psi now has a wave. And if you expand around the wave, you would get something like this. So here you have your spinors in terms of charge conjugate. And in the diagonal, you just have the usual, is the kinetic, it's exactly this. But then you get off-diagonal terms that are proportional to the interaction strength, and then the number density of Cooper pair, which is this psi taken into a wave. And the broad-angular Higgs mechanism, not only does it give, so this thing, for example, if it's charged, the size, if they are charged under U1 electromagnetism, then actually the wave has a non-zero charge, and so you would break electromagnetism, you would give a mass to your photon in such a system, and this is essentially the Meissner effect. And the broad-angular Higgs mechanism after electroweak symmetry breaking, it also gives masses to your gauge boson, but it does much more than that, right? It also gives masses to fermions, important. And it turns out that actually superfluidity would also give you mass to your fermions, but it's not a Dirac mass, it's a Majorana mass, because it's here, it's a off-diagonal term, it's not a diagonal term. And if you look at the dispersion relation of those fermions, then it would look like, so K minus mu, it kind of looks like the momentum. And then here you have the energy gap delta. So the superfluid gap delta is just going to be combination, the off-diagonal term. And so it kind of looks like a mass. and it kind of looks, it's a Majorana mass, it kind of looks like a mass, it's only around the Fermi surface, but the parallels between the Brotengler mechanism and superfluidity goes a little bit beyond just giving masses to gauge bosons. So it's just a little comment. And of course, now you might think, oh, the previous effect that I discussed, it tended to make the mass smaller, but now here it kind of seems like I have another contribution to the mass. So how do these effects compete with each other? And this is what we try to find out. So, this was a discussion for ultra-relativistic systems because here I have no mass. And of course, dark matter, it can build up from low densities to high densities. And so it's going to be nice to also try to understand what happens at low density when the system is non-relativistic. And, non-relativistic scatterings at the Fermi surface is going to be nicely described by the so-called scattering length formalism. So it's an old idea by Bethe. It just tells you that, at low energy scatterings between particles, they are very well described at only two parameters. A is the scattering length and an effective range Re that you find from the amplitude. Essentially, so whatever the potential, it might be very complicated, like complicated nuclear physics potential, etc. There is this theorem by Bethe that tells you that at low energy, everything kind of looks like this. And what's nice is that this scattering length holds a lot of information in it, and it will allow us to delimit the different kind of phases that we have in non-relativistic system. So, for example, if the scattering length is positive, and these parameters, so inverse of fermion momentum times scattering length is larger than 1, it actually corresponds to, it actually allows for bond states to form. So if the scattering length is positive, it actually tells you, okay, you can have true bond states, so really particles that are bound together in a deeper potential. And this actually tells you that you would be in a Bose-Einstein condensate phase. So this is a phase where your Cooper pairings actually are bound state, and then this thing condenses. If the scattering length is negative, it actually describe attractive interactions. And so this would correspond to Cooper pairing, and this is just BCS superfluidity. But also you can have resonances where the scattering length goes to infinity. And this is, then you get so-called unitary Fermi gas, and this corresponds to a crossover phase. And so you have all these type of superfluid phase that can be happening at low densities in the Yukawa theory. And so you can just go and start drawing the superfluid phase diagram. I give you Yukawa theory. You can go and compute the scattering length in the effective range and then just plot this thing. So, before I showed you the gas and liquid phase diagram of dark matter, but then you also have this superfluid phase diagram. So here I give you, in the y-axis is going to be the Fermi momentum divided by the mass of the mediator. It's essentially a combination. It essentially tells you that if this thing is small, then the interaction is relatively long range, because the Fermi momentum, it's a measure essentially of the interparticle distance in your system. And then here I have the another parameter that tells you about the strength of the interaction. And in this, you can go and compute the scattering length, and then for some values of this parameter is going to be negative, where then I will be in a BCS superfluid phase. Sometimes it's positive, then I will form bond state and be in a Bose-Einstein condensate. Sometimes it's you hit a resonance, and so then you have a crossover phase at all densities, and then sometimes it's zero. You have an anti-resonance, and so this gives you the peak and valley behavior of this phase diagram. And this is not just purely academic. You can accommodate self-interacting dark matter in the same way. So, for example, here I chose a special dark matter candidate. I said, okay, I have a fermion, it's 1 GeV, the Yukawa coupling is 3. And then as a function of the ratio between the mediator mass to the dark matter mass, I can redo the same plot. And then I can, of course, sometimes, since the self-interaction are strong, it's going to overshoot the bullet cluster limit on the dark matter self-interaction cross-section. And so this is where I shade everything in dashed here. And so even for as strongly self-interacting dark matter particle as you can still have theories that would reach some different superfluid phase without any problem. So okay, this is a bit ugly. I'm going to skip it, and then I just want to now give you an overview of the result without going too much into details. But the technical level is a bit complicated because the energy gaps, they are fundamentally non-perturbative quantities. And so you have to be a bit careful. One thing that I want to point out is that we worked extra hard such that everything was UV finite. So if you open a superfluid textbook, you can have the description of, for example, BCS superfluidity very easily, but then everything depends on some UV cutoff. So it's very nice if you want to obtain the qualitative understanding of parametric dependencies on the strength of on the density, the strength of the interaction, etc. But then you kind of don't know the normalization of the superfluid gap, and then it's not nice. It's not really nice if you want to really do phenomenology and assess, oh, is this effect big or small? And so we worked a little bit more to get this. Of course, again, it's a different system compared to laboratory. So there is even an academic, like purely for academic purposes, it's also nice to charter such kind of theory. So we managed to get a fully consistent description of the medium, which takes into account the first effect that I talk about, the effect of scalar density and the effect of superfluidity. We treat both effects at the same time. And even in the solutions, I described the superfluid dark matter phase diagram in a very simple way, just looking at the scattering length, etc. But actually, we kind of see hints in our solutions that this is exactly what happens. This is nice. So in the end, I started by trying to understand, okay, we have those dark side as self-interaction. Some effects were considered before. We considered for the full amount of them. We considered the fully consistent description of them. Now, what are the results? For example, like I said before, if you want to collapse a dark star inside a neutron star, then allowing for dark matter attractive interaction might be a good or a bad idea. So you might think that, it's if you add self-interaction, it's going to try to compact a little bit more the dark star, and so maybe you might reach more easily the dark Chandrasekhar mass. But it turns out that because of dark matter self-interaction, you have more, your things behave more relativistically than you thought, and then it impedes. But then once you add superfluidity, does the conclusion turns out no, because superfluidity has a very little impact on the thermodynamics of the system, and then the scalar density effect is definitely the dominant effect. Of course, this is only at the level of the thermodynamics. I didn't talk about dynamics transport. Maybe it is relevant. This is something that I don't know, and I think it's much more difficult to have access to those information. And then now we have kind of the formalism. We can crank the machine for other mediators. So I described a scalar mediator, but you can also describe a pseudo-scalar mediator, and you have other things. And so, for example, you would have P wave superfluidity because in the S wave, pseudo-scalar interaction are suppressed. And actually, there's a standard model analog of that, which is neutrino. So neutrino, they exhibit P wave superfluidity because they exchange Z boson, and it's a repulsive interaction. So now I just want to quickly conclude. Dark interactions, I think it's interesting, it's relevant. There exist lots of systems where dark matter reaches non-zero chemical potential. Then you can look at the phase diagram and draw conclusion, etc. It's a very interdisciplinary, project because you're doing dark matter phenomenology, but you're taking ideas from condensed matter physics and also nuclear physics. And if I want to conclude, it's like people have talked a lot about stuff that happens in a vacuum, and so maybe it's nice now to turn on that for dark matter you could turn on the chemical potential and see what happens. So thank you very much for your attention.
Okay. Questions here in the room or online? Yes, Jörg.
Well, thanks for the talk. Like, I wanted to ask about this mass-dependent intensity effect. So, have you studied what will happen if the mass gets negative? Because I guess if your coupling is like here, yeah, if the G is big enough, you can have tachyonic instabilities because your mass becomes imaginary, so to speak.
So I didn't go too much into detail, but actually this quantity also depends on the mass. So the number density, it's psi bar gamma 0 psi, which is just psi Dagger psi, and this is really the thing that counts the number of particles, so it's the number density. Actually, here, the thing that enters is psi bar psi. So it's not exactly the number that is called the scalar density, and it is essentially as the same form as the number density, but it's just that here you get an extra factor of mass divided by the energy. And so as the mass becomes smaller, this thing also gets smaller. And so it never crosses zero. It never goes below zero. It just tends to zero.
Okay.
It's because there is an extra factor of mass hidden here for the case of this quantity.
Anyone else would like to ask anything here?
So, I mean, I should expect this in neutron stars as well in a hot and dense or some medium, right? So, I mean, even in the core of neutron stars, you probably have an equation of state where you have some number of, or even in white dwarfs, for example, for that matter. So, I mean, should I expect superfluid? I mean, it probably depends on what your model, what you're putting in as a model, because it's a simple Yukawa model where you can form a condensate and etc. But if I were to look at something like I don't know, dark dwarf. Am I allowed to call that? I don't know. A dark white dwarf, or a dark neutron star or something. I don't know. Like, I mean, okay, probably you have to modify the model. Have to,
A neutron star, you would have ion exchange, right?
In a neutron star,
so that's your Yukawa interaction.
That's your Yukawa interaction. So I should expect superfluidity even in neutron stars, right? I mean, I don't know if people have talked about this in the context of neutron stars, because I mean, okay, the medium is probably a bit. I don't know what happens if you have too many particles. I mean, does the system then just does not go through the transition, the BCPCS transition?
So let me just say that. So for neutron star, for example, this effect is definitely relevant in neutron star. So in neutron star, you have a lot of neutrons there. If, for example, it's an all neutron star, that it's very cold and at finite density, and neutrons have strong attractive interaction. So it's pion exchange, but you can model it as the exchange of a sigma meson.
Yep.
And so it's a scalar particle. And actually, inside the neutron star, the neutrons, their mass is about 700 MeV. So it's exactly this effect that plays a role.
So that's like a color superconductivity.
So then you have neutron superfluidity in the outer regions of the neutron star. I think this is fine. People have studied. The only problem when you go to very high densities, then it's like, oh, what happens? Do I have a deconfinement? In the core, do I have neutrons? What are my degrees of freedom? So is it still neutrons, or is it now pre-quarks? And this is what most of the discussion is about. That if you have color superconductivity inside neutron star, then that would mean that I've reached densities such that I've completely deconfined my hadrons into quarks. This is the overall picture, and neutron superfluidity in neutron star happens because essentially of the Yukawa interactions, and this has effects like with the vortices formation and things like this. And so maybe if I can say also, like, we were very surprised when a Japanese group from Riken contacted us to about questions because they wanted to solve our gap equations, but in the context of neutron matter.
So I see that Bruce has a question.
So I have a very naive question, and the answer to this question may just be that I need to go away and study some more condensed matter physics, because like a lot of particle physicists, my condensed matter physics is quite primitive. When you showed that phase diagram with the alternating strips, so principally you've got sort of BCS-like behavior, Bose-Einstein condensate behavior, and crossover in between. I couldn't help notice that at one point you stated that the interaction, the pairing, is due to scattering at the Fermi surface. That's very similar to pairing of protons or pairing of neutrons in nuclei. It's complicated, but you can write down a very simple model in which scattering in relative S wave gives you the pairing interaction between protons and neutrons. And that's certainly not condensate, but nor is it true superconductivity, superfluidity either. It's some sort of intermediate. It's some other behavior, and that has to do with the relationship between the volume of the nucleus and the de Broglie length and the scattering length and so on, right? But it doesn't map neatly onto that picture. Is that just an artifact of the nucleus size? And here you're talking about a large system and everything does map straightforwardly, or is there something different about this system?
So I think
is there an explanation for someone like me with primitive condensed matter physics on what the distinctions are there?
So I think the keywords that for small system sizes, then you have finite size effects that are going to dominate, etc. But I do think to recall that for example, for very, very big nuclei, like you can, for very, very big nuclei, this kind of description, the equation of state, etc., is kind of relevant. But for for the biggest nuclei, there is some kind of, let's say, you can borrow a little bit of my presentation to understand these things. Whereas, big nuclei, you just describe them like a ball with 3 neutrons, etc. inside. And
Yep.
Just to segue a little bit into more into the relevance of scattering lengths in the nuclear physics context, that, for example, the thing that tells you that you can have a neutron-proton bound state, but not a dineutron bound state, is actually the scattering length. Like, for example, for the scattering length for neutron-neutron interaction, it's negative, and so you can't form a bond state. Whereas for neutron-proton, it's positive, and you can form a bond state. So I just wanted to throw that out there. But
yeah, no, but that's fine. That part I got. All right. So a significant part of the answer is the absence of finite state effects in the in the system that you're treating. Yeah,
and also it's purely attractive interactions, whereas in nuclear physics you also have the repulsive electromagnetic force.
Yeah. Okay. Thank you.
Anyone else like to ask a question? Online, here in this room? Okay, so then I think we can stop here and stop recording at least. Well, so thank